Hello everybody, my name is Abbas Ahmad Qasim. I'm a PhD student at the Unité de Chimie environnementale et interaction sur le vivant à l'Université de Littoral Côte d'Opale à Dunkerque, France. My PhD is under the supervision of Professor Sophie Fourmontin and Professor Jawad Zemouri. I'm happy to present our work and the results in the European project world in this presentation entitled Applications of Regenerated Waste Cooking Oil as Gas Sorbent. I'd like to begin with the context of the study, and then I will talk about the characterizations of waste cooking oil, followed by the determination of partition coefficients in static mode. After that, I will share our work and results in dynamic absorption and our work using Cosmo RS. Air pollution is one of the most serious issues we face today. In the 27 EU member states, records from 2022 show that we have 240,000 premature deaths attributed to chronic exposure to fine particulate matter. The pollutants come from several sources, such as natural sources and from human activities. We divide these pollutants into two categories: primary air pollutants and secondary air pollutants. The major primary air pollutants are the following: for instance, sulfur oxides, nitrous oxides, carbon monoxide, carbon dioxide, volatile organic compounds, particulate matter. In our study, we targeted volatile organic compounds. In fact, VOCs are organic chemical compounds which evaporate under normal indoor atmospheric conditions of temperature and pressure and are generated by numerous sources, and some of them are classified as human carcinogens. Consequently, there are numerous regulations that limit their emissions. Controlling VOCs emissions is important for environment and for public health. The primary solution is to replace VOCs whenever possible, and the secondary solution is to treat these VOCs. Several techniques are used to remove VOCs, and they are divided into two categories: destruction and recovery. Under the recovery category, we have absorption, adsorption, condensation, and membrane separation. In our study, we focused and used the absorption technique. Absorption is one of the most efficient methods to remove VOCs from gas streams. In simple terms, absorption is the mass transfer from gas phase to liquid phase when these two enter in contact in an absorber, in a column, for example. A key variable is the choice of a suitable liquid absorbent. And to do that, we have to consider HC, which is Henry Lawes constant, which must be as low as possible to have a good absorbent. Solvents and absorbents are often aqueous solutions, and they are restricted to soluble VOCs. However, most of VOCs are hydrophobic compounds. This is why there's a need for alternative solvents showing high absorption potential. An absorbent should have the following properties to be attractive for an industrial process. It should not be toxic. It should have high capacity to absorb the VOC. It should have low viscosity. It should not be expensive. Silicon oils and room temperature ionic liquids were evaluated, and they showed good absorption capacities. However, several drawbacks were presented, like their high price, toxicity, or high volatility. So in this case, we chose waste cooking oil we chose to evaluate waste cooking oil as an absorbent in biogas purification. After talking about the context of the study and the absorption mechanism, now let's move to the characterizations of waste cooking oil. The viscosity results are presented on this graph, and as you can see, for regenerated waste cooking oil and waste cooking oil presented 90 and 80 millipascal second as viscosity at 20 degrees. These values exhibited a VFT-like behavior and decreased with the increase of temperature from 20 degrees to 60 degrees, and the values of viscosity reached 20 millipascal second. On the other hand, the density was lower than 1, and there was a slight effect of temperature on the density. Let me start by explaining the partition coefficient formula. So K is the ratio of the concentration in the gas phase to that in the liquid phase. The higher the concentration in the liquid phase, the concentration of the VOCs in the liquid phase, the smaller K is, which means better absorption. To determine K, we used PRV, phase ratio volume method, which consists of adding the same concentration of VOC to different volume of water. We've done the same, but by replacing water with a solvent, for example, in our case, the waste cooking oil. And after 24 hours, we reach equilibrium. We've done GC analysis and we measured the amount of VOC in the gas phase. The partition coefficient in water for toluene, limonene, siloxane D4, decane, which are present as impurities in biogas, are presented in this table. And for instance, the HC for toluene is 0.3. Let's examine the efficiency of waste cooking oil. As you can see on the graph, the values for the K values for regenerated waste cooking oil and waste cooking oil were in the order of magnitude of 10⁻⁴ and 10⁻⁵ for limonene. We concluded that we have a reduction of K for both waste cooking oil, regenerated or not. When we compare our data to those in the literature, we found that waste cooking oil, our absorbent, is one of the most interesting and promising and efficient absorbent for these kind of VOCs. We therefore concluded that waste cooking oil exhibits very high VOCs absorption capacities. Since real gas effluents and raw biogas are composed of several VOCs, not just one, a mixture of 4 VOCs in equimolar amounts was prepared, and the results showed that we have no increase in the K values, meaning for toluene, for example, or for toluene mixture, we have K values on the same order of magnitude. We therefore concluded that we have affinities between the absorbents, and at each of the VOC compounds are maintained in presence of other VOCs, which is extremely important in real life applications. Let's now move to the dynamic absorption. The setup used is presented in this in this figure on the left. We used a syringe to inject VOCs. The VOCs enter in a bypass, and when we reach the equilibrium, we switch the valves. In this case, the VOCs enter in contact with the absorbent in the absorption column, and when we reach the same concentration at the outlet to that at the inlet, we switch the valves again, and we integrate the area under the peak in order to determine the absorption capacity. Here are the results of the dynamic absorption, and as we can see, regenerated waste cooking oil is the second best absorbent after the deep eutectic solvent C10, C12. If we take a look at the K values that we found and determined in static mode, we found that the K values for regenerated waste cooking oil are smaller than those for the C10, C12. So we asked ourselves why there's a difference between the results in dynamic mode and static mode. The answer was the viscosity. Viscosity for regenerated waste cooking oil was 6 times higher than that for C10, C12. So this influences the hydrodynamics and the mass transfer in gas-liquid contactors. This explains the slight difference in results. For the rest of the presentation, I will talk about the Cosmo-RS work. The objective was to find natural deep eutectic solvents to eliminate VOCs from biogas. We targeted 6 VOCs from different families and presented different solubilities in water. First, let me talk you through the work. First, we used TMOLEX 2024 to optimize molecular structures and identify the one with the lowest energy, meaning this implies the most stable. However, some researchers found conflicting results using TMOLEX to do this optimization. This is why we used CosmoConf to ensure that we reached the true minimum. So we used CosmoConf to ensure that we reached the true minimum, and we used these structures in CosmoTurb. The database used for the calculations contained 76 HBA, hydrogen bond acceptor, and 55 HBD, hydrogen bond donor. We had 4,200 possibilities, and to improve the performance, we added boiling point, melting point, and enthalpy of fusion. Finally, we've done calculations of activity and solubility in infinite dilution. The heat map on the right shows the results for the methyl ethyl ketone when we selected methyl ethyl ketone as VOC, and we found that the lowest value was for oxalic acid and thymol. So this at 1:1 ratio is the best one to absorb methyl ethyl ketone from biogas. We've done the same for the other VOCs, and we found interesting results. In order to understand on nanoscopic scale what's happening, the mechanism, we used M dynamics to do molecular dynamic simulations. And on this figure, we can see that we have a rectangle which contains our system. On the left side, the blue is the solvent, which is DEG, DBE, diethylene glycol, dibutyl ether. And on the right, we have the ethanol and limonene. We used this system in order to use it as a standard to compare with other deaths that we found. After a certain time, we found that the DEG-DBE is absorbing the limonene, but in order to have to draw conclusions, we had to continue this simulations and to be able to draw some more conclusions. In conclusion, we found that the studied waste cooking oil demonstrated very good VOCs absorption compared to water and other absorbents. Waste cooking oil exhibits attractive properties, low viscosity, availability, price, and it showed great promise for VOCs capture for atmospheric pollutant or biogas upgrading. Finally, Cosmo-RS is an effective tool to predict and find suitable natural compounds based this for biogas purification. I'd like to thank you for your attention, and I would encourage you to watch the other chapters. And do you think that we would be able to use waste cooking oil as an absorbent in biogas purification? Thank you.